हेलो स्टूडेंट्स। मैं डॉक्टर अंजू अग्रवाल। आज हम बीएस एमएससी केमिस्ट्री सेमेस्टर थर्ड में न्यूक्लियर केमिस्ट्री ग्रुप थर्ड पेपर न्यूक्लियर केमिस्ट्री में इलेक्ट्रॉन कैप्चर के बारे में पढ़ेंगे। व्हाट इज़ द इलेक्ट्रॉन कैप्चर? Before studying the electron capture, we have already studied about the B minus and B plus emission and have ignored the third type of beta transition, orbital electron capture. In an electron capture, an electron bound with the energy EB means the binding energy of the electron in mega electron volt is captured and a neutrino of energy E0 mega electron volt is emitted, where E0 is the difference in atomic masses of parent and daughter. Although electron capture is very common mode of decay, it escaped discovery until 1938 L. Alvarez because it is not accompanied by the emission of detectable nuclear radiation except when the product nuclei are left in the excited states so that gamma rays are emitted. The most characteristic radiations accompanying electron capture are the X-rays emitted as a consequence of the vacancy created in the electron shell from which the capture took place. The atomic rearrangements following electron capture are discussed below. A continuous spectrum of electromagnetic radiation of very low intensity is found to be emitted in electron capture processes. And in fact, in all beta decay processes, the quanta of this so-called inner Bremsstrahlung have part of energy ordinarily carried away by neutrino. The total number of quanta per electron capture disintegration is approximately 7.4 into 10 to the power minus 4 E0 square, where E0 is in mega electron volt. When nuclear gamma rays are emitted, the inner Bremsstrahlung usually escapes detection because of its low intensity. However, for EC transitions not accompanied by gamma emission, measurement of the upper energy limit of inner Bremsstrahlung spectrum is a very useful method for the determination of transition energy. In fact, it is the only direct way of measuring decay energy in electron capture. Note that to obtain E0, we must add to Bremsstrahlung endpoint energy and the mean atomic excitation energy of the product atom R1 in those events in which an internal Bremsstrahlung quantum is emitted, the neutrino energy is smaller than E0 by the energy of the quantum. The fact that monoenergetic neutrinos are emitted in electron capture decay simplifies the calculation of the statistical factor greatly, since only the neutrino phase space needs to be considered and no integration over energy is involved. Over energy is involved Again, value of FEC can be obtained from the sources quoted, or they can be approximated in the spirit of for 324 and 325, but with appreciable errors for E0 is less than 0.5 mega electron volt at high Z. Z means the atomic number. Log FEC equal to 2.0 log E0 minus 5.6 plus 3.5 log Z plus 1. Equation number 326. Capture to positron ratio. It is to be noted that whenever beta emissions is energetically possible, it competes with electron capture. Since initial and final nuclear states are the same for the two modes of decay, the ratio lambda EC upon lambda B plus is, at least for allowed transitions, expected to be completely independent of the nuclear matrix element uh, and just equal to F EC upon FB plus. Measurement of the EC to positron branching ratios thus constitute an important test for beta decay theory. In general, these ratios increases with decreasing decay energy, going to infinity when beta plus emission becomes impossible at decay energies less than or equal to 2m0c square, and with the increasing Z. The later trend means later trends yani depends on Z, comes about through the increase in the expectations value for finding orbital, especially k electron at the nucleus, and through the suppressive effect of Coulomb factor FZW on beta plus emission. The dependence of EC upon beta plus ratio on decay energy provides a useful tool for the determination of later quantity means atomic number. K upon L ratio. Whenever energetically possible, capture of K1s electrons predominates over capture of electrons with higher principal quantum numbers because of all the electrons wave functions. Those of the K electrons have the largest amplitude at the nucleus. However, at decay energies below the binding energies of K electrons, electron capture is possible only from the L 2s plus 2p M plus shell L 2s plus 2p M 3s 3p 3d and so on shells. The ratio of L1 capture to K capture as a function of decay energy has been calculated. R2 for allowed transitions. The results for Z greater than or equal to 14 can be represented by the approximate formula L1 upon K equal to bracket 0.06 plus 0.0011 Z. Bracket close. Bracket E0L neutrino upon E0K neutrino whole square, where E0L neutrino and E0K neutrino are the neutrino energies accompanying the two processes. E0L nu exceeds E0K nu by the difference between the binding energy of two shells. At decay energy is not too far in excess. At decay energies not too far in excess of the K binding energy, E0L nu upon E0k nu differs appreciably from unity, and the measurement of L to K capture ratio then permits an estimation of the decay energy by use of this equation. Note that the electron binding energies and the Z are those of parent nucleus. Z is the atomic number of parent nucleus. In allowed transitions, most of the L captures takes place from L1 to S1 half subshell. The capture probability is small for L second P half electrons and 0 for L third P 3 by 2 electrons. The contribution of M capture can usually be neglected too. Complete expression for capture in the L and M shells are available in reference M3. Extra nuclear effects of electron capture. As already mentioned, the only abundant radiation resulting from electron capture, other than the essentially undetectable neutrinos, are of extranuclear origin. If K shell vacancy is filled by an L electron, the difference between the K and L binding energies may be emitted as a characteristic X-ray, or may be used in an internal photoelectric process in which an additional extranuclear electron from the L or M or other shell is emitted with a kinetic energy equal to the characteristic X-ray energy minus its own binding energy. Such electrons are called Auger electrons. The whole process of readjustment in a heavy atom may involve many X-ray emission and Auger processes in successively higher shells. The fraction of vacancies in a given shell that is filled with accompanying X-ray emission is called the fluorescence yield, and the fraction that is filled by Auger process is the Auger yield. The K shell fluorescence yield omega K increases with increasing Z, as shown in figure. The L shell fluorescence yield in this figure, K shell fluorescence yield as a function of Z at high Z, a curve of 1 minus Wk is shown for the ease of reading. The best values give, in this case, we can say as the Z increases, Wk increases means the K shell shell fluorescence increases, and at very high K value, this is asymptotic, means this is increases slowly. The L shell fluorescence yield varies with Z in similar manner, but in several times smaller than the K yield. मीन्स जो yield है वो इसके इसी मैनर में होगी, लेकिन इसकी तुलना में ये कम होगी W ओमेगा K के कंपैरिजन में कम होगी in a similar manner, but is several times smaller than the K yield for a given Z, for about the same as the K fluorescence yield for a given electron binding energy. Knowledge of the fluorescence yield is important in the measurement of disintegration rate of electron capture nuclides. Since the radiation Most frequently detected are the X-rays. However, accurate experimental determination of fluorescence yields is difficult, particularly for WL, and theoretical calculations are often resorted to in order to supplement the experimental data. References to the experimental डाटा। आज के लिए बस इतना ही। धन्यवाद।